Welcome to Lecture 8. In this lecture, we will talk about how to compute several statistics related to a collection of n items. We will talk about how to find the maximum of these items, how to find both the maximum and the minimum of these items, and also how to find the kth smallest item. So for the first two cases, finding maximum and finding both maximum and minimum, we will analyze the upper bound and lower bound of any algorithms for solving this. And finally, for the kth smallest item, we will present an order n time algorithm for this. So let's start. Now let us take a look of the following method. We call it method 1 to find the maximum of an array of n numbers. So the input is an array S1 dot dot n, and we want to find the maximum of these n numbers. So we can first set max, which is a variable, to be equal to S of 1. And after that, we will scan this array of S, item by item, so that whenever the item that we scan has a value greater than the current max, we will now update max as the value of S of k. And finally, we will return max. So here we can see that apart from the first step, each round we will make only one comparison, taking the current item that we scan with max and compare which one is larger. So altogether, finding maximum using this method 1 requires n-1 comparisons. Okay, so let's take a look of another method. Okay, so here we have the same input S1 dot dot n, and then we find the maximum of it. So this idea here, what we are going to see is we are going to use recursion. What we are going to do here is, let's separate the items of S into two groups, the first half and the second half. We will use recursion to find out what is the maximum of the first half. So we can call this M1. Okay, so we let M1 to be the maximum of the first half. And similarly, we find out the maximum of the second half. Let's call it M2. After we get M1 and M2, we will compare M1 and M2. And whichever is larger, this should be the maximum of all the n items. So how many comparisons are there if we are using this method? Okay, so let us analyze it by defining T of n to be the number of comparisons to find max of n items using this method 2. Then when we have just one item, then we don't need any comparison at all. So T1 is equal to 0. But for Tn needs to do what? So first of all, we divide the array of n numbers into two groups. So one group has n over 2 items and the other has another n over 2. To be more specific, one group has the floor of n over 2 items and the other group has the ceiling of n over 2 items. Now because we are going to use recursion to find the maximum of each group, so the number of comparisons will be T of n over 2 and T of n over 2 here. We obtain the maximum of the first group, we obtain the maximum of the second group, and then we still need one more comparison to find out which of these two maximums is the true maximum. So we will have a +1 here. Now this is something that we have seen before, and then we can find out exactly the closed form for this Tn. So it turns out that Tn will be exactly equal to n-1. To see why this is true, you can try it by yourself. It is easy to use substitution method to show that this is correct. Now again, this method 2 also uses exactly n-1 comparisons. So the question here is that it seems like method 1 and method 2 are already quite clever. And we want to ask, will there be a better algorithm that uses strictly fewer than n-1 comparison, but still can find the maximum? But here we will see that the answer is no. The reason is that, so we can imagine that finding the maximum when we are doing comparison is like we are playing a game that we have two numbers that they are fighting each other, so that the larger value stays and the smaller value will be removed. So in such a case, so each match between the two numbers will have one winner and one loser. Now for a number to be the only possible maximum number that we have, we must have all the other numbers, all the non-maximum numbers, to have lost some time during some comparison. It is because if there are more than one number which haven't lost at all, then we cannot be sure that which of these two numbers or which of these no loser, so they haven't lost, will be the maximum. So the key point here is that every non-maximum number has to lose at least once. But as we have mentioned, each match, each comparison creates only one loser. So in other words, we must have at least n-1 comparisons involved. And this is not just the worst case situation. It is even in the best case for any algorithms. If it is correct, it must make at least n-1 comparisons in order to create n-1 losers. So this is the lower bound analysis of finding maximum. And the number of comparisons is n-1, matching the upper bound result. So that means that the two methods that we have seen, so this is the method 1 that we have seen, and this is the method 2 that we have seen, they are already the optimal algorithms for finding maximum.